Satellites are bounded with Earth. And why they are bounded with Earth? Because of the gravitational force. So today we will discuss the Kepler's law. Kepler's law of planetary motion. We will discuss Kepler's laws of motion. Three laws are given by Kepler. Kepler's laws of planetary motion. Hiba, do you know what is ellipse? Do you know what is circle?
Yes.
Do you know what is ellipse?
Yes, sir.
So there is a requirement of knowledge, prior knowledge of ellipse we should have. So I think I should tell you first what is the ellipse. So basically, very simple. Ellipse. So first, okay, I'm telling you what is ellipse. Like circle is there, no? In the same way, ellipse is also there. This type of figure, oval shape type. And what is circle? Circle is like this. This is circle, no? This is circle, and this is ellipse. So what is the speciality of this? We will see. So the focus of us will be on ellipse. So this is ellipse, and so this is the center of the ellipse. Suppose this is the center of the ellipse. Like center of circle is this, and this is the radius. But here the things are different. In case of the ellipse, there are two focuses. Uh, this is the center, and at a distance of AE, A into E. I will tell you what is A and what is E. So first, I think I should tell you what is A and what is B. So this whole length, na, from
So E is eccentricity.
yeah, centricity. So from here to here, this distance is A. Okay, and from here to here also, this distance is A. And from here to here, not from here to here, from why we are studying the ellipse? Okay, because you will know why we are studying the ellipse today. This distance is B, and this distance is also B with this distance. Okay, so this distance is A, this distance is A, this distance is B, this distance is B. So A is known as semi-major axis. A is known as semi-major axis, and 2A is known as the major axis. B is known as the semi-minor axis. And 2B is known as the minor axis. So now from here to here, this distance is b. From here to here, this distance is b. This distance. Okay. So suppose this is one point, and the coordinate of this point. Okay. So after that, we will discuss later what is the coordinate of this point. Here will be somewhere. Here will be focus. Here. This is one focus, and this will be at a distance of AE from the center. A distance of A into E, and E is the eccentricity. Okay, E is the eccentricity, and this is one of the focus. Suppose this is F1, and another focus will be at the same distance AE from the center. AE. Okay. Now it is very easy. This distance is this F1 and this is F2. So you can say these two foci are there. This is one focus. This is another focus. And equation of ellipse. Equation of ellipse is x square is equal divided by a square plus y square divided by b square is equal to 1. And for circle, if circle, this is the circle, no? For this circle, you can write the equation of circle x square plus y square is equal to r square. Okay. There is a relation between B, A and E. So B square is equal to A square 1 minus E square is there for ellipse, and E is known as the eccentricity. E is known as the eccentricity. This eccentricity is basically the measure of how ellipse means with respect to the circle, how this shape is changed. Hello. So we are discussing ellipse. What is your name, Faraz? We are discussing the ellipse.
Yes, it's Aisha.
Yeah, you are Aisha. Okay. So Aisha, we are discussing the ellipse. So like circle is there and ellipse is also there. So this is ellipse, white color, and in case of the ellipse, this is 2a. A plus a 2a. This 2a is known as the major axis, and half of it is known as the minor axis. In the same way, this is b, and this is also b. So this 2v, b plus b is known as the minor axis, and 2b only is known as the major axis, semi minor axis. And this is center, and this is one of the focus. So the distance between the center and the focus is AE, and there are two foci in case of the ellipse. So equation of ellipse is this, and there is a relation between BA and it means the major axis, means the minor axis, major axis, and eccentricity. So this eccentricity value is in between 0 and 1, and if this eccentricity value is approaching to 0, so this ellipse will approach or ellipse will become circle. If this eccentricity value is approaching to 1, so it will be elliptical, more elliptical. Okay. After that, okay, so this is about the ellipse. can anyone tell me the, okay, we will discuss that later when we will discuss the Kepler's first law. So first you should take the screenshot of this, then we will discuss the Kepler's first law. Both of you, please take the screenshot, then we will discuss the Kepler's first law. Till now, what we did, what we were discussing, that we are considering the circular orbits only. Satellite, we know that is revolving in a circular orbit, and somewhere we assume that, I think, uh, Earth is revolving around the sun in a circular orbit, but this is not true. Okay, so now take this screenshot. Then we will discuss the Kepler's first law. Okay. Shiva, done? Okay.
Yes.
Okay, now Kepler's first law, and this is all. This is the last topic of this chapter, Kepler's laws of planetary motion. So basically, it is Kepler's laws gives the information how the planets are revolving. Okay, so Kepler's first law. So first law is all planets. You can take the example of Earth. Earth is also a planet. All planets revolve around the sun in closed elliptical path. Closed elliptical path. So the planets are revolving in this elliptical path, not in a circular path. Okay. This is the first law. And sun is at one focus of ellipse, and sun is at one focus of ellipse. So now we will discuss this. What is this? This is the ellipse, and major and minor axes are there. I told you what is this distance, what is this distance, what is this, okay? So this is one of the focus, suppose. And here is what? Here is sun. Sun is situated at one of the focus. So I have taken at this focus. You can take on this focus also. Sun is situated here, and this is the focus. And suppose this is the planet P. P means planet. So this planet is revolving around the sun in this path like this. In this path like this. In the elliptical orbit. So this whole distance is what? This whole distance is A. This distance is A, na? From center to the periphery, this distance is A, na? So this coordinate will be A, 0, and this coordinate will be minus a comma 0, because this distance is also a, and this distance is what? This distance is AE. This distance is AE. So this, the coordinate of the focus will be AE comma 0. Okay. AE comma 0. Okay, so I have already written this. Okay. So this is the planet, this is the sun. Suppose this planet is revolving anti-clockwise like this. So now this coordinate will be a comma 0, and this coordinate will be minus a comma 0 if this is origin, and this coordinate will be AE comma 0, and this coordinate will be minus AE comma 0. So this is the first law. The planet revolves around the sun in closed elliptical path, and sun is at one focus of the ellipse. Okay, so suppose this is the focus of the ellipse, which is a distance of AE from the center of the ellipse. Okay, now Kepler's second law. Kepler's second law. Earlier, what we discussed, when the satellite is revolving around the Earth, so that satellite is revolving with the orbital speed. V is equal to under root 2g, V is equal to under root gm by r, and that speed is a constant speed. But the planet revolving around the sun is moving with not a constant speed. The speed is variable. So Kepler's second law. Kepler's second law. So Kepler's second law says that planets do not revolve around the sun with constant speed. Planets do not revolve with constant speed around the sun. Around the sun. Basically, this is the indirect form of the Kepler's law I am writing. Okay, indirect form. Exactly, the statement is something different that we will discuss. Planets do not revolve with constant speed around the sun. Okay. So we should write this like this. I should take this here. Oh. Planets do not revolve with constant speed around the sun. Planets move faster when they are planet moves faster when it is near to sun, and planet moves slower when it is far from sun. So this is a relative statement. So you can see if the planet is suppose here, and there is one planet P and this time this planet P is at A position, and A position is this. Now this planet is revolving. After some time, this planet is here at B position. This planet is at B position. So the speed of this planet will be more at A position as compared to the B position. Okay, the speed of planet will be more at A position because it is nearer to the sun here, and at this point the planet is far from the sun as compared to this point. Okay. So now the what is the exact statement? The exact statement is this of the Kepler's second law. Okay. The aerial velocity of a planet is constant. Aerial velocity of a planet is constant. Or you can say that a planet sweeps equal area in equal time. Equal area in equal time interval. In equal time interval. Now what is this? So basically what we should do now? This is basically the observation. So it should be here. It should be here. Okay, now again we will take one ellipse and we will understand. So this is the ellipse and okay. So this is sun at one of the focus and this is the planet. So now this time sun I am drawing like this. S means sun is on the focus. This is the planet. So for example, this planet P is revolving around the sun and this planet moved from this position to this position. This planet moved from this position to this position. Okay. So what is the concept of area swept? Area swept will be this value. This will be the area swept by the planet. Suppose this area is dA. This area is dA and this area is swept in time interval dt. So we are taking this planet is moved. dA is very small area. I am showing this as a large, but this area is very small because it is covered in dt small interval of time. Okay. Now there is another thing that suppose if the planet is moving from suppose here to here, and here also the time taken by the planet is dt sub. Time taken by the planet is dt. dt means a small time. So in that case, in moving the planet from this point to this point, time taken is dt, and in that time dt, this planet covers this dA area. Okay. Now, in moving the planet from this point to this point, time taken by the planet is dt. Time taken by the planet is dt. What will be the area? According to the Kepler's third law, the planet swaps equal area in equal interval of time. In equal interval of time, it will swap equal area. So here also the area will be dA. So what can we say? We can say that this area will be equal to this area. If it is covered in equal time. Suppose for covering this area, it is taking unit hour, 1 hour. So for covering this area or sweeping this area, the planet will take, sorry, for in 1 hour, this much of area is covered. Okay, A area is covered, suppose in 1 hour, A area is covered when the planet is moving from here to here. Another you can say, when the planet will move from here to here, in 1 hour it will swept again equal area. Okay, A area it will swept. So basically what is constant? dA by dt is constant. Rate of sweeping area is constant. And that rate of area sweeping is known as the aerial velocity. So dA by dt is equal to constant. dA by dt is constant, and this dA by dt is what? Aerial velocity. So dA by dt is constant means you can say now wait, we can change our definition for a definite time interval. So this is for a very small time interval dt. So now I will say that uh, in time t1, the area swept by this planet so will be suppose a1. Okay. Now for this planet t2, this planet from here to here, in moving from here to here, this planet is taking time t2, and area sweeping is a2. Means this area is a1, this area is a2, and time for the motion of the planet from here to here is t1, and for this planet the time is t2 in moving from here to here. So what is the meaning of the aerial velocity constant? Aerial velocity constant means this ratio of area by time, means a1 by t1 is equal to a2 by t2. You can take other area or other time also, that will be equal to a3 by t3 and so on, a4 by t4. All these things are constant. So now tell me one thing, both these areas are same. Both these areas are same. Here, here, suppose this is covering, again I am saying a1 area in time t1. Earlier time was same. Okay, that is why area was same. So this area is not equal to this time this area. Okay, because this planet is covering this in time t1, and this is the planet, this is area is covering in time t2. So here in this case, it is better to take one more point. The planet is moving from this point to this point, this point to this point. So this is another area, and this another area is covered in time t3, and this area is a3. Okay, in area is a3. Planet is moved from this point to this point, from here to here. Now, if this area a1 is not equal to a2 is not equal to a3, all these three areas are different. A1 is not equal to a2, it not is not equal to a3. T1 is not equal to T2 is not equal to T3. So in this case now what will remain constant? Aerial velocity will remain constant, means A1 by T1 of this, A1 by T1 from here to here, A2 by T2 from here to here. Aerial velocity na, area versus area divided by time is area velocity. So A2 by T2 is equal to A3 by T3. So here the velocity of motion of the planet will be different. Okay, the velocity of the motion of the planet will be different. So here if the velocity is v1, here if the velocity is v1, here is the velocity is v2, here the velocity is v3. So v1 is not equal to v2 is not equal to v3. The reason is that from moving this planet from here to here, it is taking time t1, and this covering the less distance in time t1, and this covering the more distance in time t2. So basically you can say that we cannot say that speed is same. So that is why the speed of the planet, its speed of a planet is different when the planet is moving in the elliptical path, and when the planet is near to the sun. When planet is near to the sun, it will have more velocity or speed. When planet is far from sun, it will have less velocity, okay, or less speed. First note down this, then we will discuss. Take the screenshots. Then completed, Hiba
Yes, sir.
and Aisha completed.
Yes, sir.
Okay. Done?
No, sir. Wait.
Okay.
Done, sir.
Okay.
Done, sir.
Okay.
So can you scroll up one further? Done, sir.
So you have to remember here. Done this?
Yes, sir.
Okay. So note down this also. So basically this V1 and V2 and V3 is representing the speed of a planet at a particular point. Okay. So during this motion, the speed will change. So here this speed or velocity is representing the speed of a planet at any particular point. Okay. So aerial velocity is constant. Okay. Aerial velocity means area swept divided by time is constant. Area swept divided by time is constant. So aerial velocity is dA by dt, area swept in a particular time. Now, after that, we have one concept of angular momentum. So here is sun, suppose. And this planet is revolving around the sun in the elliptical orbit, and sun is at one of the focus. So the velocity of the planet will be like this. Velocity of the planet will be like this. This is the velocity of the planet. Suppose this is, okay, velocity of the planet. And this is ellipse. Okay. So this angle between the velocity and this angle will be theta. Okay. This is the radius vector. This is distance r, suppose. This is distance r. So the angle between r and v, r vector, and this is v vector. This is r vector. When you will extend this will become, this is basically the r vector. Okay, we are extending it. So the angle between the r vector and the velocity vector is theta. This is not 90 degrees, this is theta. So angular momentum of this planet, angular momentum of this planet will be, angular momentum is represented by L, and L vector is, this is the vector quantity, and it is given by r cross the linear momentum. So it will become r cross linear momentum is mass of the planet into velocity of the planet, and when you will open the cross product, it will become r mv sine theta. Okay, the angular momentum of the planet about the sun. This is the angular momentum about the sun of the planet. This is given by r mv sine theta, and this is constant. Angular momentum is constant. And why the angular momentum is constant? This planet this time is here, and this planet is this time here. So the gravitational force will be in this direction, and we are finding the angular momentum. Oh, sorry. This is the angular momentum. This is the force of gravitation about this uh, axis. Okay. So if you will calculate the torque, if you will calculate the torque of this planet, about the sun. So torque is given by, torque is also a vector quantity, r cross f. So one thing I told you when we were discussing the uh, rotational motion, when we were discussing the torque. So if the force is passing through a point, and about that point you are calculating the torque. So that torque will be zero. So force torque due to this force will be zero. Means this torque will be zero. So if torque is zero, means the angular momentum is constant. So that is why I was saying that angular momentum of the planet is constant. How I am saying that if torque is equal to zero, angular momentum is constant. You can relate this with, basically this is Newton's second law in the rotation, and you can relate it like this. If net force on the system is zero, so what we say? The momentum is constant. Linear momentum is constant. Okay. So if in the rotational system, if torque is equal to zero, means angular momentum is constant. So angular momentum of this planet will remain constant. Okay. Angular momentum of this planet remain constant. One more point is there. The aerial velocity dA by dt is equal to angular momentum divided by 2 times of mass of the planet. L is what? Angular momentum of the planet about sun. M is the mass of planet. dA by dt is equal to 2m. dA by dt is equal to 2m. After this, there is the third law of the Kepler. For example, what is the third law? This is the sun, suppose. Here is the sun, and a planet is revolving, suppose here. This time the planet is here and at a distance of r. At a distance of, this is the planet, and this planet is at a distance of r, small r. So this, you can take this is r1, and this is planet P. This is revolving around the sun. Okay, we know that the planet revolves around the sun in the elliptical orbit. So this is the planet P, and this planet is revolving around the sun. Okay, and this planet is here, and this time the radius, this distance is r. Okay, this distance is r1. Okay, another planet is there. This is the sun. Another planet is there, and this another planet is revolving in another, suppose, smaller orbit you can take. At a distance of r2. Okay. And time period of this planet P1, this is planet P2. Basically, this is one planet P1, and this planet is revolving around the sun. This planet is also revolving around the sun because planet revolves around the sun. And this time the radius is r1, and this time the radius is r2. So time period of the planet is suppose t1. T1 is the time period. Time period means time to complete one revolution. And for this planet, the time is T2. So basically, the third law says that T2 by T1, T2 by T1 is equal to R2 by R1 and cube of this. And this is the square of time period and cube of this. From here, na, you can say that time period of square of the time period is directly proportional to the R cube. Okay. So this is the third law. But there is one more point here. This R is not constant. When the planet will be somewhere here, this R will change. So basically, this is true when we are considering the motion of the planet as circular motion. Okay. Exactly, it will be like this. Time period of the planet, square of the time period of the planet is directly proportional to A square. Okay. This is the exact. But then why we are writing this? Because when we will solve the question, we will use this, not this. To study the geometry of a circle as compared to the ellipse is easy. That is why we have written the Kepler third law in this form. Okay, so you should note down this and okay, so take the screenshot of this. Done? Done?
Answer.
Oh, okay. So basically, this is the exact Kepler's third law, but for solving the numericals, we will use this, or you can say this. What we are considering exactly this planet is revolving around the in a elliptical path, but we will consider the planet is revolving around the circular path. Okay. So you should write this also. Okay. So now we will solve one of the question on this. Okay. If distance between the earth, now come to the questions, numerical. If distance between earth and sun were half of its present value of its present value, the number of days in a year would be, the number of days in a year would be. Option A is 64.5 days. Option B is 129 days. Option C is 182.5 days. Option D is 730 days. So they are saying this is the sun, and this is the earth here, and this earth is revolving around the sun. And the distance between the center of the sun and the earth is suppose uh, d. D is the distance. This is the initial condition. Now they are saying if this distance becomes somehow half, somehow if this distance become half, suppose this becomes d by 2. So in a year, how many days that time will become? Now we know that in the present condition, how many days are there in 1 year? 365 days, na? Okay. 365 days. What is the meaning of those 365 days? Means time period of the earth, revolution around the sun, basically 365 days. So time period we have in this case 365 days. So now you can see here, without assuming that the earth revolving around the sun in a spherical path, we cannot solve this question. Okay, it's very difficult to solve. So we will assume here that earth is revolving around the sun in a circular path. So we will apply this formula, T2 by T1. So basically we want to find T2, and R2 and R1 is given. Okay, what is R2? R2 is d by 2. R2 is d by 2 and R1 is d. R1 is d. So T2 by T1 is equal to R2 by R1. So T2 we have to find. T1 is given as 365 days and square of it, and this is equal to R2 by R1. R2 is d by 2 and R1 is d in cube of this. So you will have T2 square and 365 square, and this is equal to d and d will be cancel out. So what you will have? You will have 1 by 8. From here you will have t square is equal to 365 square means 365 multiplied by 365 divided by 8. So from here you can get the value of t. T you will get 365 divided by 2 under root 2. So you can multiply this with root 2 and with root 2. So you will get 365 divided by 2, 2 to the 4. Here will be root 2 and here will be 4. So approximately this answer you will find 136.4 days. So nearest answer, you have to check the nearest answer in the option of 136. Not this option will be incorrect, this will be also incorrect, this will be also incorrect. So basically 129 days you have to correct, means answer will be correct. One more question we will do on the aerial velocity. Got it this question? You have to apply this formula. This formula T2 by T1 is equal to R2 by R1 and square of time period and cube of radius. Hiba and Hiba, hello.
Okay.
Getting enough?
Yes.
Have you taken the screenshot of this?
Also.
Okay, so take this screenshot. Scroll down.
Yes.
Yeah, take this screenshot. This one. One more question we will do, and after that, this chapter will be finished. Scroll down.
Yes.
Okay, now you can take the screenshot of this.
Yes.
Okay, take this screenshot.
Yes.
Done?
Done.
Okay, so last question of this chapter. Okay. So in this question, it is given that the ratio of Earth's orbital angular momentum about Sun to its mass is 4.4 into 10 to the power 15 meter square per second. The area enclosed by Earth's orbit is approximately okay. So this we have to find in meter square. We have to find the area of the Earth swept, area of the area swept by the Earth. We have to find. So what we will do, we will draw the diagram. This is the elliptical path, and somewhere here is Sun. Suppose this is Sun and this is Earth. So this Earth is revolving around the Sun. So what they are asking, area enclosed by Earth orbit. Area enclosed by Earth orbit means they are asking the total area, because this Earth will move from here to here to here to here. To complete one orbit, the Earth will be at the same position. So basically, you will get the total area. So this total area we have to find. So area of ellipse is equal to pi into AB. So we do not have A. A is the length of major axis, length of semi-major axis, and length of semi-minor axis is not given. A and B we do not have. So we cannot calculate the area with this formula. But we have one other formula. Aerial velocity dA by dt. We did here. dA by dt is equal to L by 2m. And what is dA by dt? Aerial velocity. So the aerial velocity is equal to L divided by 2m. dA by dt is equal to L divided by 2m. L is the orbital angular momentum about the Sun. M is the mass of the Sun, mass of the planet. Okay. So here Earth is the planet having the mass, suppose m, and angular momentum is L. So ratio of m by L is given already. L by m is given already. Ratio of angular momentum to the mass. For what? For Earth about the Sun is given in the question, and that is 4.4 into 10 to the power 15 meter square per second. We know that dA by dt is equal to L divided by 2m. So from here L by m value we can put. So it will be 4.4 into 10 to the power 15 divided by 2. So we will get 2 by 2, 2.2 into 10 to the power 15. Okay. And this value will be again in meter square per second. Meter square per second. Now to calculate this total area, there is a requirement of total time. So total area is suppose A and total time is the time period. and this is equal to this value 2.2 into 10 to the power 15. So total area swept in a total interval of time, and this is t, and time interval or time period for the earth revolution around the sun is 365 days. So t here is 365 days. So we can convert 365 days into second. So it will be t into 2.2 into 10 to the power 15. So t is 365 days. You will multiply it with 24 hours. Again you will multiply it with 60. Again you will multiply it with 60 seconds. And this is multiplied with 2.2 into 10 to the power 15. So you will get the answer in meter square. Okay, so in this way also we can solve the question. So the here what we have applied, the aerial velocity dA by dt is equal to the angular momentum of the planet about the sun divided by mass of the planet. Okay, so please note down this, and this chapter is finished now. Please note down. Okay. Take this screenshot. Okay, after this we will meet in the next class with the new chapter. So now which chapter is going on in other class? Are you joining that? In
Yes,
the
sir.
other which chapter is going on?
Thermodynamics.
Thermodynamics.
Yeah.
So okay, so accordingly I will start the chapter. Okay,
Yes, sir.
in the next class. Okay, so please join the next class. This chapter is finished. So we have done all the topics related to your syllabus. Okay, I have tried whatever the knowledge I have